Let's now introduce technology to the Solow-Swan model. So this is typically done in 3 different ways. So one way is called the Higgs neutral technology, where technology is just this variable a that multiplies f of kl. So how does that relate to the model we had before? So you can just imagine that a was equal to 1 and constant, so we didn't have to care about it. But now a will be allowed to vary over time. The Higgs-neutral technology is also sometimes referred to as the total factor augmenting technology, since it multiplies the whole production of K and L. Now we have also the capital augmenting technology, referred to as Solow-neutral, where we just have technology that improves the productivity of capital K, but does not affect the productivity of labor. And finally, the labor augmenting technology, referred to as Aaron neutral, where technology augments the productivity of L, but doesn't affect K. So I already hear you ask, but professor, this is confusing. What is the truth? Well, I don't know. It depends, because technology is such an elusive concept. It's difficult to measure, and it's possible to think of some specific technology that has this effect, or that effect. It depends on the definition. And in terms of the model, we're going to see that it doesn't have really strong implications in terms of if we choose this version, or that version. Yeah, so just before, one thing we have to keep in mind is though that f still has its property of having constant returns to scale. So if you multiply k and l by some constant, then it's like multiplying af of kl by this constant. So here, for instance, in that version, f would have constant returns to scale with respect to ak and l. And here it would have constant return to scale with respect to k and al, but not the 3 of them. Otherwise, it's not constant returns to scale anymore. Okay, so just before we move on, so can you think of some examples of Solow-neutral or Aaron-neutral technology? I'll give you some time. Time's up, so let's go ahead. So capital augmenting technology, something that augments the productivity of capital. Well, one I think easy example that we can think of is computing. So computers used to be very slow, and then over time they get more and more efficient. So this makes their use more and more useful. And here's a way to measure computing power. So calculation per second per 1,000 US dollar. So this is from Ray Kurzweil's website. So for those who don't know, Ray Kurzweil now works at Google on their artificial intelligence neural networks on Gmail, I think in particular. So he's very smart. He has like 20 honorary doctorates, and he makes these wild predictions about the future of mankind and technology. And so this graph is very interesting. We often think that that computers were invented, say, in the 1940s by Alan Turing, but actually it shows that no, before that we had electromechanical technology, and after that we had other technologies, and then integrated circuits and Moore's law. But that so the power of computing has really increased at an exponential rate for as long as we had computers, basically. So I invite you to check him. He's very interesting. So that's capital augmenting technology. And then labor augmenting technology. This also is quite easy to think of an example. So here is one. education. You could also think of IQ, for instance. So it's hard to say whether investment in education has been exponential over time, but still it's pretty striking that since the 19th century, so public spending as share of GDP on education has increased very much, from almost nothing to now above 30% in France. It's not to say that France has the best education, but you know, education is taken very seriously in France. Okay, so now we introduce technology in the Aaron-neutral way, in a more formal way. Let's go ahead and define our labor augmenting technology. Y equals to F of K AL. So we keep the same exogenous constant population growth rate N. And now, instead of having essentially A equals to 1 and being stable over time, we are going to allow A to change and make our lives easy by assuming that it's an exogenous constant technology growth rate, delta A divided by A, which we will simply note G. So G is some positive constant. Also, we could note it G of A, but so know that if it's just G, then it's just the growth rate of technology by itself. And now let's define the new concept, which is the technology augmented labor. Why do we do that? Well, look at what we have done. In a sense, we have exactly the same model as we used to have. It's just that before we had only L and now we have only AL. So the trick here is to just, it's just a matter of definition. So let's say that instead of caring about how many people are in the workforce, we care about how many efficient people work. So the number of technology augmented worker or technology augmented labor, which we write L tilde equals AL. So don't be scared by L tilde. It's actually there to help us to make our lives easier. Because now the only thing we really have to do is to redefine all the other variables in terms of L tilde instead of L, and we're done basically. So let's go ahead and do that. So instead of considering capital per worker, we consider capital per efficient worker. So K divided by L tilde is small k tilde. And output per worker is replaced by output per efficient worker. So Y divided by L tilde is equal to small y tilde. And now the important question is then we had the growth rate of labor. Now we need the growth rate of efficient labor. So what is the growth rate of efficient labor? I give you a couple of seconds to think about it. All right, so let's just write it. G of L tilde is equal to what? Well, we have to look at what L tilde is. So L tilde is the product of A and L, and both are increasing. So if we remember one or two things about growth rates, since this is a multiplication, then we just add up the growth rates together. So it's equal to the growth rate of A plus the growth rate of L. And we know what they are. So the growth rate of A is just G, and the growth rate of L is just N. So what does that mean? It means that in a sense, there is some degree of substitutability between technology and workers. In a sense, imagine that an efficient worker has productivity A equals 2, and an unskilled worker has productivity A equals 1, then you can see that there's really no difference between having one skilled worker or two unskilled workers. So what do we know about the capital requirement of more workers? Well, more workers need more capital to work with. So more efficient workers is exactly like even more workers. So it's going to need even more capital. And technology growth is like, in a sense, a faster population growth. So everything we had deduced about population growth is just going to be magnified by the growth of both technology and the labor force. So now let's go ahead and define our new state variable. We used to have one state variable that was k, small k, that was capital per worker, and now you can guess more or less where we're going. So the new state variable is going to be this, so the capital per efficient worker. And everything is going to be well defined in terms of this new variable. So what's the new law of motion? Well, it's delta k tilde, which is going to be a function of savings times f of k tilde, which is going to be the output per efficient worker minus what was it? It was depreciation delta plus n times k. But now we have the growth rate of efficient worker, so L tilde, multiplied by capital per efficient worker. So this is our new law of motion. All we have done is basically change n for g of L tilde, change k for k tilde, and nothing has changed otherwise. And we can note that we can already substitute g of L by g plus n. And now, what is our new steady state? Well, the new steady state is simply defined by delta k tilde equals 0. So it means that SF, or let's use that one. So SF of k tilde will be equal to delta plus g plus n times k tilde at the steady state. So it's not necessarily it's a steady state for k tilde, but it's going to be a balanced growth path for all the other variables that we care about. Last thing to define is the new golden rule. Note that we can't define it in terms of consumption per capita, since it's never going to go to a steady state. But now the new steady state is consumption per effective worker. So again, all we have to do is a simple change of variable, and we can see what happens. So I'm not going to go through the same optimization, but you can see it for yourself. We can just write it down. So the new golden rule is that the derivative of f with respect to k tilde is equal to delta plus g plus n. And again, the intuition here is that in terms of capital per effective worker, then the more the population goes up, and the more technology advances, then the least we should strive to have much capital per effective worker because the amount of effective worker increases so fast that it would lead to basically over-invest. So it's best to invest a bit less. All right, so now we have to look at the new growth rate where things get interesting. It is now time to see if we can save the Solow-Swan model. So let's start with Kaldor fact number 2. Capital per worker has grown at a sustained rate. Is that going to be true or false? So let's just start with stating what it is. So capital per worker, its growth is G of small k, capital per worker, and then of course we care about this in the balanced growth path. So think about it for a while. I'm not going to give you the answer right away. Okay, time's up. So what do we know? Well, let's have the same strategy as we had before. So first of all, we know one thing about the long run. We know that the growth of capital per effective worker is 0 on the balanced growth path. All right. So let's start with that. Well, what is capital per effective worker? It is equal to capital divided by AL. And can we glean some insight about this? Well, yes, it's also equal to capital over labor. So capital per capita or per worker divided by technology. So we can now use what we know about growth rates and deduce what happened in the long run. So we know that in the long run, we're going to have that the growth of capital per worker, per effective worker, is going to be what? The growth of capital per worker minus the growth of technology. And this has to be equal to 0 on the balanced growth path. So what we know is that the growth on the balanced growth path of capital per worker is equal to the growth of technology and is equal to G. So at last we find that in this version of the model with technological growth, then this leads to accumulation of more and more capital per worker. And this is specifically labor enhancing technology. So it's because we get more and more productive workers, and it is more efficient to equip these workers with more and more capital. So that's why the capital stock per worker always has to be increasing. So if you didn't get the first one, don't worry, here's your chance to make up for it. So let's check now Kaldor fact number 1. Labor productivity has grown at a sustained rate. So what is labor productivity, you ask? That's a good question that we should already know. So, well, first of all, it's a growth rate. So we are looking at the growth rate on the balanced growth path of labor productivity, which is output per worker, so small y. And so we want to know if on the balanced growth path this is positive or not. Think about it. Okay, time's up. So this one is a bit more involved because we again have to look at something intermediate. So we know explicitly what is capital per effective worker, but now we have to know that in fact we are we know one or two things about output per effective worker, which is a function of capital per effective worker. the same way that output per worker is a function of capital per worker. So it's 1-to-1. And if this grows at rate 0 on the balanced growth path, then output per effective worker has to grow at growth rate 0 on the balanced growth path. So it means that and so that's one thing. Second thing is, what is then, that we use a second fact, what is output per effective worker? Then it's equal to total output divided by technology multiplied by the number of workers. And you can already guess where this is going. So here we get Y divided by L, so output per worker. So we get that this is equal to Y divided by A. So output per worker divided by technology. And now we have everything we need. So on the balanced growth path, G star of Y tilde is equal to what? Is equal to the growth rate of Y minus the growth rate of technology A, and it is equal to 0. So it means that the growth rate of output per worker is actually equal to the growth rate of technology again, and it is equal to G. So again, what drives output per worker? What drives productivity? And in the end, here it plays the same role as GDP per capita. So it is technology. We see that in a sense, capital can adjust itself to the growth rate of population and the growth rate of technology. So it comes along for the ride, so to speak. But in fact, here it's what is really important to improve prosperity in a country is improvement in technology. That's really a deep lesson about the Solow model. Kaldor fact number 4, the ratio of capital to output has been stable. So what is the ratio of capital to output? Well, it's equal to K divided by Y. And the question is, has that been stable or not on the balanced growth path in the Solow-Swan model? So think about it. You can do it in many different ways. Okay, time's up. So here's a very simple way to do it. So capital divided by output is also equal to capital per worker divided by output per worker. So it's equal to small k divided by small y. And what do we know about the how small k and small y evolve on the balanced growth path? Well, the growth of small y is g, and the growth of small k is g as well. So since both grow at exactly the same rate, then their ratio is never going to change. It's always going to be multiplied by the same number. So we know that they are exactly going to be stable. So that was an easy one. Now we go to the more complicated ones.